This lesson, we're going to start looking at different types of reactions in more detail. So what we'll cover is some background information on synthesis, decomposition, and combustion reactions, and then we'll practice some problems to see if what you've learned has sunk in and whether you can predict the right types of products for those reactions. So in your previous science course, you should have learned a little bit about reactions, but today what we're going to do is take it a step further. We're going to learn how to identify them and look at different patterns that you'll see. So if you're asked to predict what types of products might be produced, you'll have a better understanding of how and why that will happen. You'll want your periodic table and your ion list handy because we're writing chemical equations and balancing them. So those are two tools that you'll always want to keep handy. To start, what we're going to do is look at synthesis reactions, and we'll quickly go over the general pattern for a synthesis reaction. Synthesis means you're making something new. So here we're making a new product. When we look at it in terms of a chemical reaction, you're going to have one or more reactants, and they're going to combine and give you one new product. In some cases, there are multiple, but we're going to focus on, for the most part, one new product being formed. Here, if we look up at the general formula, it says A and B. So whatever elements A and B are made up of, they all recombine into one new product. So here, if we're looking for a pattern, there's two reactants, and you're getting one product. So we're going to see that play out in a couple of different ways, and we'll look at a few different scenarios as we start to look at our synthesis reactions. So we'll start off with the simplest one. What if you want to make a very simple binary compound? That will be composed of two elements in their natural states. So as an example, to give you an idea, let's say we took some nitrogen gas and some oxygen gas, and they react and they give you a nitrogen oxide. This is nitrogen monoxide that's produced. You can see when you look at the new compound, it's only made up of nitrogen and it's only made up of oxygen. Those are the two elements there. But when you write out one of these formulas, you have to remember a lot about your nomenclature and formula writing. These two are both diatomic gases at room temperature. That's why we see N2 and O2 here. We can also make other new compounds, but they're a little bit maybe more complex. Maybe it starts with a compound combining with another element. Here they're made up of the same element. This has chlorine in it, and this is chlorine as a pure element on its own. And it makes another compound with more chlorine in it. So more atoms and definitely more complex. Sometimes, though, you can see some that follow some typical patterns. So there are many that have patterns. We're going to look at a couple in more detail together. So in general, what happens with these ones, you can have two compounds combining, and they make one big complex compound. So let's take a look at a pattern first. The pattern here, one of the compounds is going to be a nonmetal oxide. The other compound is going to be water. So compound 1 is going to be nonmetal oxide. Compound 2 will be water. And the more complex formula that's formed here is an acid. So let's look at an example where we're going to get an acid being produced. So first, what is a nonmetal oxide? Let's make sure we understand what that is. We know what nonmetals are. So any nonmetal that combines with oxygen is classified as a nonmetal oxide. So here you've got carbon dioxide. That's a nonmetal oxide. Here's your water molecule, and it's going to produce your acid. This acid here is carbonic acid. How do you know which acid is going to form? Well, on your periodic table, you know you can get the charge for hydrogen for that part of the acid, but on your polyatomic ion list, you're looking for the most common ion that's on there that has carbon and oxygen in it. So when you're looking at that one, you should probably see that there's a carbonate ion. And so the carbonate ion will form and it will bond with the hydrogen and it will make the acid for you. Here's another one, a little bit different. This time, instead of a non-metal oxide, we've got a metal oxide reacting with water. So, similar to what we just saw up here, we've got a metal with oxygen. Your other reactant is water. But this time, instead of making an acid, you make a base. And if you remember a little bit about bases from grade 10, bases have the hydroxide ion in them. So if we were to look at an example here, here's your nonmetal oxide, Na2O, sodium oxide. Here's the water, and they combine to give you the base. So what you need to do when you're trying to figure out what your base is, you're going to take your metal, and it's going to have the hydroxide ion. That's how you figure out what base you have. So if we look here, our metal is sodium, and the oxygen and hydrogen are going to come from the rest of the other compounds. And then when you're writing out your base, you're doing your crisscross between whatever metal you have and whatever non-metal you have to come up with the formula. Let's take a look now at some decomposition reactions. So we'll do the same thing. We'll take a look at the general pattern first. So decomposition is kind of like the opposite of synthesis. Here you're starting with one larger compound, or can be complex or non-complex, but it's larger. And it's going to break apart into simpler components. The A and the B could be elements. They could be an element in a compound. It could be two compounds. That can vary. Okay? But here the pattern is you have one reactant and it breaks apart into two or more products. So we'll look at some examples together and also look at a few that are a little bit more specific, and those are ones that you'll need to be familiar with. So what are our different conditions? First, let's take a look at a very simple one, and this is pretty much the exact opposite of our first synthesis example that we looked at. Here you have a binary compound. It's made up of two elements. When it decomposes, it's going to break apart into nitrogen gas and oxygen gas. If you look here, there's two elements in that binary compound, nitrogen and oxygen. So if they're going to be stable on their own, they have to take on their most stable configurations over here. It wouldn't just be nitrogen and oxygen as single elements. We know those ones are diatomic. Now, one thing that is often needed for decomposition that isn't shown here, but for decomposition, you often need extra energy. It's an energy requiring process because you're breaking something down. So things like heat, light, anything like that, etc. And to show that, sometimes what you'll see over arrow for reactions, sometimes you see a triangle, and that means that there's heat or energy involved. Or sometimes they'll even use plus heat as part of the equation over with the reactants. So sometimes you'll see that in there, but if it's not included, it probably is required for that to happen. It's not going to generally happen on its own for a lot of the cases. So now let's take a look at a few more examples, ones that are a little more specific. So here we've got one that you should be familiar with. What happens when metal nitrates decompose? So first let's make sure we understand what a metal nitrate is. Here's your metal, which is sodium, and here's your nitrate, polyatomic ion. That's why this is called a metal nitrate. Sodium nitrate is a metal with a nitrate ion. When it decomposes, it makes metal nitrites and oxygen gas. Because this metal, in our example was sodium, that doesn't change. So you can see sodium here and sodium here. But the nitrate changes from ATE to ITE. And if you remember from your nomenclature, that means that it has one less oxygen in it. So you can see over here that this has one less oxygen, NO3 to NO2. And then that other oxygen is lost and it forms oxygen gas because, again, this is a diatomic molecule at normal room conditions. You're not just going to see oxygen, it's stable as oxygen gas. Here's another example of a compound containing a metal decomposing. For this one, you can see again we have a metal, but the metal this time is not combined with nitrate, it's combined with carbonate. So here we have sodium, sorry, we don't have sodium, we have calcium, and we have the carbonate ion. What happens when it breaks down? It's going to make a metal oxide. So the metal is calcium oxide in this specific example. And it also forms a gas. This time, though, it's going to make carbon dioxide over here. So the calcium still sticks with some of the oxygen, but the carbon and some of the oxygen is lost as carbon dioxide. Let's look at one more specific example of decomposition reactions. Again, this involves a metal. What happens this time if you have a metal hydroxide and you want to decompose it? So here's your metal and here's your hydroxide ion. In this example is calcium hydroxide. This one also happens to produce a metal oxide. So you see between the two here, they're actually the same product, calcium oxide. But the other product is different this time. Because it's a metal hydroxide, it ends up producing water instead. So these are three ones you should be familiar with. They're a little bit more specific in terms of decomposition reactions. Finally, let's take a look at combustion reactions. So what happens in combustion reactions? In general, you're going to have a reaction of a substance, but one of the reactants has to be oxygen for it to fall into this category. They'll make different types of oxides, and energy is released in the process, sometimes as light, sometimes as heat, things like that. If you're still not really sure what combustion is, think about burning fuel. So like burning wood on a fire, that's a great example of a combustion reaction. You're reacting with the oxygen in the air, it's burning and producing flames and heat. So that's a good one to think of. There's two types of combustion reactions, complete and incomplete. So what we're going to do is look at complete combustion first. Complete combustion, when you hear that term, it means that there's lots of oxygen available. So with lots of oxygen available, the burning will keep going and going until all of the other reactant is used up. In this example, we're going to look specifically at burning something called hydrocarbons. Hydrocarbons are used for lots of fuels. They make oils, they're in your gasoline, and like the name says, a hydrocarbon is something that only has hydrogen and carbon in it. When you have complete combustion of a hydrocarbon, there's only two products that are produced. One is always water, And the other product, the second one, is always carbon dioxide. The amounts of each will vary because the hydrocarbon will change, and then when you balance your reaction, it will change. But as long as you have a hydrocarbon and lots of oxygen, these are always the only two products that you will get. So as an example down here, we've got CH4. This is also called methane, but this is your hydrocarbon. So this is a hydrocarbon. Carbon and hydrogen only in the formula. It's combustion because you're adding oxygen. Anytime you have hydrocarbon, you always get carbon dioxide and you always get water. Sometimes what you'll also see with combustion, sometimes they'll add in plus energy or plus heat here because it is produced, but it's not always indicated there. Here, because of the type of hydrocarbon you have and how you balance the reaction, you have one molecule of carbon dioxide and 2 molecules of water produced. If you change how many carbons and hydrogens over here by having a different hydrocarbon, when you balance, you'll find the numbers will change and will be different, but you'll still always have carbon dioxide and water. There are other examples of complete combustion that don't involve hydrocarbons, and these are some things that you've probably seen in your daily lives. So other things can undergo combustion to form what we call stable oxides. So things like metals plus oxygen, those will give you metal oxides. And you can think of those things like rust. So rust is a good example where iron reacts with oxygen and it forms iron oxides. Any kind of tarnish sometimes, or a film that can coat different metals, it's because of oxidation reactions. But up to this point, you could also classify this as synthesis. When you look at what's happening here, an element plus an element gives you a compound. So these ones could be classified as combustion because it's specifically oxygen involved, but it also is often just classified as synthesis as well. So in this example, think rust, think tarnish. Those are places where you've seen this type of reaction in action. Last type of reaction is still with combustion, but this one has a slightly different process and condition. This time we have incomplete combustion. Incomplete is different because one small factor here. You still have oxygen around, but it's insufficient. So that means you're lacking oxygen. There's not a lot, enough to get the reaction going, but maybe not for it to sustain and burn very well. So if we go back to the idea and we think about hydrocarbons, we know when we burn hydrocarbons in combustion reactions, we said you're going to get carbon dioxide and water. But this time, if it says there's insufficient oxygen or it's lacking oxygen, you get 2 more products being formed. One is going to be carbon monoxide, which is a deadly gas, and the other one is going to be carbon. Think of carbon as like black soot or just carbon solids. This can vary, but we're just going to refer to it as carbon or carbon solids. So if we looked at an example of incomplete combustion, down here, this would show you the pattern, and you can see it looks a lot more complicated. There's a lot more numbers for balancing, and there's a lot more compounds in here. So let's break it down for you. This is your hydrocarbon. This is the oxygen gas. So you can see these are still your same 2 reactants, but here somewhere in the question it will say there's a lack of oxygen or insufficient or something like that. It's lacking. So what do we get? we get carbon, and here we're just writing it as a solid. Here's your carbon monoxide. Here's your carbon dioxide. And here's your water. It can be as water vapor, as a gas, or liquid water, depending on the conditions that are there. But in general down here, this is the general pattern. Any hydrocarbon with oxygen, but a lack of it, for it to go to completion, you get carbon solids, carbon monoxide, carbon dioxide, and water. And then when you go to balance these, they'll have all sorts of different numbers. And sometimes when you balance these ones, you'll find there's more than one way that will work. Because there's carbons and oxygens all over the place, often the balancing can vary depending on what you decide to do. So now that we've gone over 3 types of reactions, what we're going to do is try some practice problems. Can we identify what type of reaction we have? And then can we figure out what the product should be and balance the equation? So, if you have your notes printed off at this point, I would pause the video and try and see how many you can do without help. If you don't have them printed off and you're following along, try and do one at a time to see if you can figure out what's going on, and that'll help you understand faster and pick up the concepts a little bit easier. So for all of these examples, what we're going to try and do is figure out what type of reaction we have and predict the products of the reaction, and then finally balance the reaction. So I'll walk through the first one with you to give you an idea. So when I look here, I have 2 reactants. This is an element and this is an element. So I want to think, when I have an element plus an element, what type of reaction do I have? For today, it's either synthesis, decomposition, or combustion. Combustion I know has to have oxygen. This isn't oxygen and this isn't oxygen, so it's not going to be combustion. Then I have to decide, is it synthesis or decomposition? Decomposition takes one big compound and breaks it apart into smaller ones, whereas synthesis will take 2 smaller elements or compounds and combine them into one. Here, I've got 2 reactants to start off with, so this is leading me to believe I have synthesis. So that would mean I'm going to make a compound, and I'm going to write over here, this is going to be a synthesis reaction. So, if I have 2 elements, that means my product is going to be a combination of potassium and bromine. When I go to write my product, I have to start from scratch. Potassium and bromine, they both have charges of 1 when I look at their formulas on the periodic table. When I do the crisscross, the 1s disappear, and I'm just left with KBr. So that is my product. It's nice, I don't have to do anything here with my coefficients or numbers yet. So here's my element, here's my element, here's my one new compound. Now I take a look and see if it's balanced. 1 potassium, but there's 2 bromines and only 1 here. So when I go to balance it, I need to put a 2 here, so there's 2 bromines. But I've changed the number of potassiums, so that means I need to put a 2 here. So this is what we're trying to do with these problems. First, think about what type of reaction it is, and then see, based on that, is it following a pattern that we learned about? And if it is, can I figure out what the product will be? So here's one for you to try. See if you can pause the video now and figure out what type of reaction this is, what the product could be, and if it needs to be balanced, go ahead and do that. Hopefully you've given this one some thought, so let's start taking a look. When I look here, I've got sulfur trioxide. Sulfur trioxide is a non-metal oxide. And I have my non-metal oxide. It's reacting with water. Now, if you got stuck on this one and you didn't realize you had a non-metal oxide in water, before hearing the rest of the question, go back to your notes and see if you can find the pattern for non-metal oxide plus water, what type of reaction it is, and see if you know what the product is. If you think you've tried this out and think you know the answer, keep listening. So when I go and look at my notes, I see there is a pattern, non-metal oxide plus water. That is a type of synthesis reaction. And when I look more closely, non-metal oxides plus water produce acids. So I know my product here has to be an acid. Acid, we know, is hydrogen plus another ion. So I know with my acid, when I'm thinking about my product, hydrogen has to be there. I know it has a charge of 1. Then I go to my periodic table. SO3, I'm looking for a polyatomic ion that's similar to SO3. I go down my list and I should find the sulfate ion. Sulfate ion is SO4 and it has a charge of -2. So if I'm making an acid between hydrogen and sulfate, the 1 will come down with the sulfate ion and this 2 comes down here beside the hydrogen. Here, I want to get rid of these numbers, so we're not going to keep them in there. It's not helpful for us right now. And then since I have an acid, I'm going to put AQ beside the formula because I know that's what I need. So now I have my non-metal oxide reacting with water, giving me my acid. This is sulfuric acid. Once I've done that, I need to check, is my reaction balanced or not? So take a quick look and see, is this one balanced? And if not, put your coefficients in. After you've taken a look, you can probably see that all of the elements are actually already balanced on both sides. So this one we don't have to do any more work for. It's already balanced the way that it is. Now that we've done 2, here are the next 2 for us to try. Hopefully now you're starting to get the idea of where we're going. So pause the video, see if you can figure these ones out. And again, when you're ready to check, unpause and we'll walk through the answer together. Here when I look, I've got 1 compound to start. No other clues. It doesn't really fit into any of the other patterns I'm seeing. So here I'm going to think I'm dealing with decomposition. I've got 1 compound, it's going to break apart into more. This type of compound, if I want to be more specific, is binary. 2 different elements. So here it starts off at 1. We know binary compounds are going to break apart into their elements. So an element plus an element. What are my 2 elements? I've got nickel, and my other element is oxygen, and on its own it has to be O2. Now that I've got that in there, I know I have decomposition, my compound's broken apart into 2 elements, then I need to balance the equation. It's definitely not balanced as is. So if I want to balance this one, I would need to put a 2 here, a 4 here, and a 3 here, and then everything would be balanced. Next example, again, I've got 1 reactant. 1 reactant leads me to believe this is decomposition. But it's a little bit different here. This one fits into one of the categories we've looked at. Lithium is a metal, and the other ion is a nitrate. So then I want to think, well, what's the pattern that we learned when metal nitrates decompose? You get metal nitrites, and you get a gas being formed. In this case, it's oxygen gas. So when I go and look here, I have lithium nitrate. If I'm making a nitrite, it needs to be lithium nitrite, LiNO2. And I know my formula for oxygen gas. It's O2. And then I want to try and again balance this equation if it's needed. So taking a look at it, it's definitely not balanced. So to make sure this is balanced, I've got to put a 2 here, and I've got to put a 2 here. And now everything looks good. 2 more examples to finish things off. These are ones with combustion. So this could be an example that you might see. It might say complete and incomplete. So complete, remember, means lots of oxygen. Incomplete means a lack of oxygen. Here's your hydrocarbon, and here's your hydrocarbon. So what's going to happen? Let's look at our pattern first with complete. Hydrocarbon plus oxygen, we said was going to give us 2 specific products. Think about what they were. You're going to get carbon dioxide and you're going to get water. Doesn't matter, again, this can vary, but you're going to get those 2 products. When you have incomplete combustion with a hydrocarbon, the pattern starts off looking the same, but instead of only 2 products, this time you can make up to 4. Carbon dioxide, and water will always be there for both types. But if it's incomplete, remember you get carbon monoxide and carbon. So now knowing this pattern, let's see if you can write out the formulas for all of the products for both of these and try and balance them. That's the tricky part. These ones tend to be a little bit tougher to balance. So try that out, see what you get, and we'll pick up the answers next. Okay, so formula for carbon dioxide is CO2, and we know water, H2O, and this one's definitely not balanced. So after you've given it some time to balance, you should get a 5, a 3, and a 4. Again, if you haven't tried the next one, pause it now to give yourself a chance. Write the products down, try and balance it. This one is trickier, but I would still really want you to try so you get that practice. The more you practice on these ones, the better you get. All right. Here's your formulas. CO2, H2O, CO, and C. Now, there are a few ways to actually balance this one. I'm only going to show you one, but if you've done it another way and you're pretty confident that that's the answer, you're probably right. I think there's about 3 different ways I've seen this one balanced. So, one way is to have a 7 here, 2 here, an 8 here, a 2 here, and a 2 there. So hopefully that gives you an idea about synthesis, decomposition, and combustion reactions in more detail. how we can look at them to identify them based on their reactants and products, but also to try and figure out, well, what are the products that we expect and how to write out their formulas. In your practice for homework, there are more specific cases than we have gone over in our lesson. To summarize that, it's in another file within your notes, but this is what it looks like. And this is a good study sheet for synthesis and decomposition. So I'd highly recommend that you take a look through these ones to see if you can apply this knowledge while doing your homework. We've got some that we've seen and others that are a little bit different, but they're all patterns that you're probably familiar with. Same thing for decomposition, but again, these ones are, again, a little more specific. We went over metal carbonates, we went over metal hydroxides. Another one that falls in that category are metallic chlorides, metals with the chlorate ions. They give you a metal chloride and oxygen gas. Acids can also decompose. They will break apart into water and a non-metal oxide. We've seen some simple decomposition where we have a binary compound into elements. Okay? And then there's even some, we don't really focus on these as much here, but some decomposition require electricity. Those are called electrolysis reactions, where you can take compounds and split them into their elements. So water breaking apart into hydrogen and oxygen gas, or an ionic compound breaking apart into its two elements, like sodium chloride into sodium and chlorine. So these are some good ones to keep in mind and review. And when you're doing your work, there'll be a few more I'm sure you'll encounter and learn about.